Okay. Sarah asked, can we do problem number 5? And I responded, no way, Jose. We're going to do something that's virtually identical.
Okay.
So that is the problem that we looked at. Okay, that's weird. I had that problem before and then it started working later. At the end of the class period. So calorimetry problems. Here's the steps to doing the calorimetry problems. Identify each item and write the equation for heat. And then I have the equations for heat written there. And then I have my preference of how to do that. But if you're doing a calorimetry problem, it needs to start with it's insulated, thermally isolated, so you don't have heat flowing in or out. So the net heat is 0. And then you add up the heats, solve for whatever is unknown. So given that, here's the problem. And now I want you to work as a table. And of course, Diana, you join another table rather than work alone. On how to solve this and ask me questions as we go through. And this is completely analogous to problem 5, except for the thing that Mr. Chapman was pointing out with problem 5. Problem 5, it does not completely melt. This one here, I believe it does, although I haven't worked this problem out recently. Paper gel. Yeah, working on this the same. So maybe Joey, David, and Robotics, since they don't have 2. And since assumedly Diana's going to be working with these 2. Yeah.
So we're going to go to 20 to negative 5 to 25.
Now you can work Sandy.
Do we need writing the can you go back to these steps?
Yes.
You are doing social.
Or I can go to the other app and shrink down so you can see both at the same time, which is probably best.
Can you also put up the
Maybe.
specific heats of ice and everything else that we need?
Yes. So
I don't have those good for ice.
the specific heat of water is 4.186.
Bro.
Yeah.
Yeah, it's kind of equal.
Was it 79.7 joules per gram?
Sure.
While you guys are working, I'll look that up to make sure. CI? Specific heat of ice. Okay, which one do you use, Christina Burden?
We were always like 1.5.
Pull it out and like just look at
So now you look after icing water, right?
Yes. And then sulfur.
Oh, yeah. I got my units confused. Excellent. That would have been in kilocalories, that number.
This is grams or kilograms?
All of these are per gram. They're joules per gram.
Yeah, we don't really change. Yeah, I just realized that.
Is it gonna be deal?
The one in this gave us.
How many equations do you need, everyone?
I don't know.
Is changing.
Can we put the Q's equal to each other?
Yeah.
Put the Q equals MCAT equal to the Q is equal to M.
Oh wait, we can solve.
Well,
for-
you have to add all of the Q's. All of the Q's added together equals
But how do you
zero.
know the Q is different than the Q's?
Okay. Sarah asked a question, and I will give you a little bit of ways of thinking about this. If we have looking at the ice, if we plot the temperature versus heat that flows in, initially the ice is in the solid phase. It has specific heat of sea ice. And so you're going to have initially Q ice is equal to MI sea ice. Agree? So if I plot that on this graph, I'm going to have a line that looks like this with the slope, which is change in temperature over heat. So I'm going to have that slope initially. And how far can that go? From my starting temperature, of course, for ice, the starting temperature was -5. What's the maximum temperature for the ice? At 1 atmosphere pressure? 0. So that stops when you get to 0. Then what happens when you get to a temperature of 0 is you continue to put heat in. It starts melting. And so during melting, that's supposed to be red. And so I'm going to put subscript M there is equal to the mass of the ice times the latent heat of fusion for the water at constant temperature. So it's going to go like this as you continue to add in heat until it completely melts. Then what happens when it completely melts? You have Q ice, liquid equals mass of ice, specific heat. Now it's not ice anymore. What is it called once it's melted? Water. And I'll call this delta T. I'll just call delta T 3 so that we don't confuse the delta T ice with that. And so that's going to be going something like this with the slope equal to 1 over M ice C water. So that's what's going on if we look at just the ice.
So I can get more information on the problem.
Oh, you wanted to look back at the problem? Yeah. Okay. So that's what's going on. We have 3 heat equations for the ice. 1 heating up to 0, 1 melting, and then 1 heating up beyond 0. Now, as I discussed this with David before class, and he was then mentioning to others, in your homework problem 5, it's fundamentally the same problem. But in homework 5, remember I told you I just assume it's going to completely melt? hence my picture here, assuming it completely melts. In homework 5, it actually intimates that it does not completely melt. Because if you look at parts B and C, it asks you how much of the ice melts, which implies it's not 100%. So I always make an assumption, and with my assumption here, I think this is going to turn out. If you use this assumption in the homework problem, you're going to find that your answer for temperature final comes out to be a negative, and you'll be like, what? That means it didn't melt? Then you know that your assumption was wrong. So if we do this problem, we work it out, and we get a positive temperature, we know we assumed right. If we get a negative temperature, we know we assumed wrong. So that's how you would test the first part of problem 5. Then the rest of it is exactly like we're doing, except for if only some of it melts, you change this mass of ice into just the mass that melts. So these are 3 of your equations. What is change in temperature for the ice going to be? Go ahead, say it out loud. It's going to change by 5 degrees because it's temperature final. What's the final temperature for the ice? 0. Minus the temperature initial. What's the initial temperature? -5. So 0 minus -5. Change in temperature for the ice is up 5 degrees. Change in temperature 3 is going to be temperature final minus the temperature that the melted ice started at. What was the starting temperature for the melted ice? 0. Because the frozen ice started at -5 and ended at 0. Then it melted, and then this melted ice started at 0 and went up. So we have those 3 equations, and then you have a 4th equation. What's the 4th equation going to be for? All of these were for ice. What's the 4th equation going to be for? Water. And so we're going to have Q for the water is mass of the water, C of water, change in temperature for the water. Change in temperature for the water is it ends at temperature final because they end up in equilibrium, which means everything is at constant temperature. And what did it start at? It's the only number you can read. 20. Now, because these are changes in temperature, you don't have to change to kelvins. If you change to kelvins, everything would still work out. So you can do a change in temperature problem either way. So those are the 4 equations you need. So the underlying equations here are the ones you need. Yes, Anna.
I'm a little bit confused. So are we saying that the last equation we can just plug in for like mass of water, the C of water, and then the delta TW is going to be the negative 20 degrees Celsius?
Yes. Well, or no. It's temperature final minus 20 degrees Celsius.
Okay. I was like, yeah, I don't understand. Okay.
So what do you do at this point? Okay. Well, you do. I actually put numbers in the equation at this point. It's easier, typically. But you add up all of those heats, and what do they have to add up to?
0.
0, because we started by saying it's an insulated system, isolated, so we have no heat flowing in or out. So when you have a final temperature, let me know.
Yeah, I got that first too.
You don't have a final temperature yet.
All right, yeah. Let's work. It's the- What? What do you eat? Change your back, busy. That's good. Right on. Here, move. Got it yet?
No, I might have delta TW. The result.
Cheap. It's a big thing. Hey.
I get negative 10.5.
No, it was.
It's not sure. It's
Why? It's not on the
it's not finished. My fault. Evil. It's like,
I'm not on this.
But it's like,
Yes.
nah.
That's what fine.
So you have to solve.
Yeah, we add up all the Q's.
You said cool, but I couldn't be here, so I'm feeling like.
But how do you,
I
for either,
couldn't set this up.
you couldn't solve for delta TW or delta T3 then, could you?
Well,
Two equations.
delta T3 has temperature refinement. Delta TW. So both of those are functions that
Right? So you can't solve for both.
well, when we add up all the
Yeah, how, I know to solve for all of the Q's.
well, after we find temperature refinement, we could go back and solve for the Q's, but we're not solving for the individuals. We're solving for temperature refinement.
Right.
So all of them.
So if you add them all up, you have 4 different Q equations. So you add them all up, instead of equal to 0.
At this point, so. Specific heat of water is 1.2.
EL is, no.
It's up there.
That's again, that's 334.
You have 145 and 7970.
Shut up on my phone.
Or Q by.
What did you get? 7.
970.
Where did you get that? Was that the
The Q of ice.
Are you working your way through it?
Yeah, probably is equal to N of ice.
Guys, you're not working on the problem.
I got 30.
I was, he was. This is how we work. So like, what you want to do, basic things for them.
The 33.
I think so.
Oh, where did I get 70? I got the L of B.
Oh, you.
Probably.
You said.
Okay, so we said.
Come on, man, something.
So what?
Use your final engineer, build me a back. I'm gonna build a robot to take your job. Get him to build a speaker, bro. Alright, what's up? It's this one. Oh, you're talking about that. You need the latent heat one for the ice. Is that up there? Yeah. That left. It's easy then. It's usually 100. Ice is 2.
No. Check my message.
Check up here. Relax.
Which ones?
Looking for final temperature or heat?
You're looking for the final temperature.
So how much heat you got?
Don't know.
It's fine, I see.
No.
Oh, we don't care.
We know that the sum of all the heats, because it's insulated, the sum of all the heats is 0.
Oh, so you just, I'm plugging 2 plus 4. It's 2 plus 4. 7. I just did.
Did you get 1.5 on?
I am just adding all up now and trying
Sure.
T3.
For which one?
Super water, so Archie,
No, the delta T would be T final minus 20. Because you're starting off with an initial temperature of 20 and it's increasing some other temperatures. So your delta T is
So you get a number for this one and for this one. This
we
one
don't know
here,
yet. That's what we don't know.
this one here
So then ours
is going to be
changed
T
in
final
temperature
minus,
3.
or excuse me, not T final, it's going to be T.
So that one would be T sub F minus 0 degrees.
Like that.
Because in the first one, the delta T ice, that's it's after 0. That's the final, that's not the final heat of ice, that's final ice. So it's 0 minus whatever the initial was. And then for the Q of ice melting, you don't worry about
This,
it
yeah,
there.
this one.
But for the liquid ice, we know that it starts at 0 degrees because once it's melted, it's 0 degrees and it's going up to some unknown. So it's 200 minus the initial.
Well, that's from what I got.
It's so
2.73 degrees. Wrong.
First, it has to be positive. So it's up to your.
Is it gonna be bigger?
It shouldn't be bigger than the water temperature.
It shouldn't be.
Okay, see, I have this too, 34.45. Then,
I like distributed.
wait,
What? Oh, that was.
So you carry those two numbers out.
Yeah, I just. So 1.5.
on the floor.
And then 100 times 234.
So those three lines, so Boltzmann, part 1, 3, 10, part 1, 3, part 1, 4 equations. So this is the one for water, this is the 3 for ice.
Great, so I got the one for water. That one's there. And
Maybe it doesn't.
then
Because, I mean, looking at your work, as long as that is 350 times 4.18, which.
Yeah, it's just the final temperature, whatever that is, minus 0 degrees. Because we started at 0 degrees once the ice turned.
okay, and then we're using that.
So
I think you're right. I think it doesn't all melt.
Okay.
I think that's,
And then it's just the
that's right, because you got non-solvents there. You got a negative answer, which I.
What's your negative answer? 62.
No, you know it's gonna be between -5 and +20.
I did
Ooh,
about 100.
come on, dude.
Plus
What number?
100.
That's what I did.
Plus 100 times 100 plus 350 times 156 times 200 times 0.
Yo, no.
Okay, so then, okay, do I just go leave? Yeah. And then I would do. So that's what I did. I'll try.
I think distributing might be the biggest, but I don't even know if I did it right, to be honest.
So just suck it up.
I got -2.
Like 2.1.
72.
I can't see where you would have made
That's what I got.
So I'm gonna.
Wait,
I know.
you think she's right?
I think she is. I think it doesn't fully melt. I think this is exactly like. Yeah, that's what she got too. I think this is exactly like problem 5, just different numbers.
What is I do wrong?
I don't know. Let's do it now. I know at least 2 people worked all the way through, 2 groups. Okay, 3 people, they all got the same temperature. But -2.7 doesn't make sense, right? So that tells you our assumption was wrong. What was the assumption we made? That the ice completely melts. So now we have to go back and say, okay, the ice doesn't completely melt. And so my equations are going to be, now it's only 3 equations. Because now I'm going to have, well, again, we have to modify. Q ice 1 is equal to the mass of the ice times C of the ice times delta T of the ice. which is, and I'm actually going to put numbers in here because this is the one time in life where I find it easier to put in numbers. 100 grams times 2.090 joules per gram degrees Celsius times 0 minus a minus 5.00 degrees Celsius. And so if I multiply all of that through, I have 500 times roughly 2. It's just a little bit bigger than 1,000, but what is it?
1045.
And then Q ice 2 is going to be the mass that melts. It's not the mass of ice. It's not the mass of water. It's the mass that actually melted, which is what you're looking for in problem 5, multiplied by the latent heat of fusion. So now my unknown is mass melt instead of temperature final. And then my third and final equation, Q water is equal to the mass of water, C water, delta T water equals, what is it, 350?
Yeah.
And since we now have determined that it ends at 0, temperature final is 0. So now we multiply that through, and
Wait, I'm confused. How do we know that it's 0?
because we had a negative answer for the first time, and that was nonsense, so it means that it only partially melts. If it partially melts, you have liquid water and ice in equilibrium, which has to be 0. Right, so it's from the result of our first calculation that we know this. So what do I get when I multiply that through? Because I know everybody calculated that already. It's how much? She's not speaking loud enough for me to hear.
Yeah.
Negative 29.
302.
Okay, so we only have 3. Why don't we have a fourth one now? Because it doesn't completely melt, so we don't have a term for warming up the melted ice. So now we add these all together. Sum of the heats equals 0 equals 1045 joules plus 334 joules per gram times the mass that melts minus 29302 joules. Right, so you see why I put in the numbers where I could, because this is a kind of ugly equation if you put in all the variables.
It
So-
should actually be 29323.
Oh, so now I just move these two numbers to the other side of the equal sign. So if I take 29323 minus 1045, what do I get?
Well, let's use it 29302.
Okay, we can't determine, we can't agree on what that number is. What'd you get?
Shouldn't it still be like the same concept though, and it's like a really good number?
Yes.
Okay, so 29325 minus the 1045.
Which is?
28280.
So the final step, divide by 334.
28280.
228, oh, I missed a 0. So divide everything by the 334.
85
Grams. Looking at my units, the joules cancel. I'm left with 1 over grams. 85 point what?
Sorry, 84.67.
84.7. So the mass that melts is 84.7 grams. And that's exactly how you do problem 5.
It can be that, right?
It can, because we started with 100 grams,
Okay, so it's saying that a good portion of it melted.
A good portion of it melted, yes. Just because it's funny, somebody came up with 42 of our 0.14 grams of ice melted in problem 5. You shouldn't have more ice melt than you have ice to begin with. So make sure you check that. So any questions about the process? Right, we set this up in class on Friday, but we didn't have time to complete it. I want to make sure you had time to go through and complete it and see an example, because let's face it, problem 5 is the hardest problem in the homework, isn't it? All right, with no questions, I shall move on. So we've gone through, answered all of those, solved for the final temperature. Final temperature turned out to be 0 degrees Celsius with 84 point, what was it, 7 grams melt. Okay, ideal gases. Everyone has dealt with ideal gas law, I'm pretty sure. So what we're going to do is talk about ideal gases and what makes an ideal gas ideal. Because I know when I was in high school and when I was in chemistry, we didn't talk about what was ideal. We just said this is ideal. So what makes a gas ideal is, number one, atoms and molecules don't interact unless they collide. And if they collide, they have purely elastic collisions. Now, in reality, nothing's purely elastic. But this is an approximation of what would be ideal behavior. Number two is that the atoms and molecules have no volume. So they're points moving about. And of course, that doesn't make sense either. We know that atoms and molecules take up volume. So this is an approximation. How are we going to determine if a gas is going to behave ideally? Those are ideal behaviors. We want to say, is a gas going to be approximately like atoms and molecules don't interact unless they collide, and atoms and molecules have no volume? We can make conditions to simulate being approximately that. So first, for the atoms and molecules to not interact, what that fundamentally means is if the atoms come close to each other or if they actually collide, their change in energy is going to be very small compared to their energy. Now, we've learned about energy, kinetic energy specifically. What macroscopic measurement, we call these actually variables of state, tells us about the average kinetic energy of the molecules?
I'm not like mentally here right now, so if that's wrong, we can push further.
Okay. Yeah, that's not right. The variables of state are pressure, volume, temperature, and the number of molecules. Which one of those relates to the average kinetic energy of the molecules? Temperature. Temperature is telling us about the average kinetic energy. The higher the temperature, the higher the average kinetic energy. And so if we want to approximate that they don't lose any energy as they pass near or collide with other molecules, then we want the percentage, how much it does lose, to be small compared to the total energy. So we want the energy to be high, which means the temperature needs to be high. To make this approximation valid, we say the temperature has to be far above the condensation temperature. So for water, for instance, the condensation temperature of water is 100 degrees Celsius. If you have steam at 105 degrees Celsius, that's not far away. So it's not going to be behaving like an ideal gas. But if you have steam at 800 degrees Celsius, oh yeah, that's far away from 100. It's approximately, well, it's less than 3 times and more than 2 times. Now, if you think about that, how is 800 less than 3 times 100? It's a true statement. I did not lie. I did not err. you're comparing temperatures, you have to use kelvins. You have to use an absolute scale. So 100 is 373. 800 is 10,000, well, 11,000 something. No, it's 10,073. So 10,073 is less than 3 times 373. But it's more than 2 times 273. So it's between 2 and 3 times the temperature. So temperature being far above the boiling temperature, that's going to behave ideally by the first one. Now the second one, atoms and molecules have 0 volume. Once again, we do a comparison. What's the average size of a molecule compared to the space between them? If the space between them is very large compared to the size, then it's approximately true that they have no volume. And so if you have a low density for the gas, that means you have a big space between the molecules, and they're going to behave closer to ideal. So the 2 practical conditions for an ideal gas is low density and high temperature. And high temperature is defined relative to the boiling temperature of the substance. So if you take something like oxygen, oxygen boils at somewhere in the ballpark of like 4 kelvins. So room temperature for oxygen, that's way above boiling temperature. Of course, oxygen is only 21% of the air. The rest is nitrogen. What's the boiling temperature for nitrogen? You don't know it. 77 kelvins. So room temperature is once again well above the boiling temperature for nitrogen. Hence, air behaves like an ideal gas, at least by the first rule, if we are in a normal temperature situation. Room temperature, air is the ideal gas. Now, there are things that go into the ideal gas law. And I have to be completely honest, I never pay attention to Boyle's law, to Charles' law, to the Gay-Lussac law. I simply use the ideal gas law. But the development is actually something that's, I think, useful to know. So it was Charles, I'm sure it's not pronounced that way because it's French. It's like Charles or something like that. He was studying what happens if you keep the pressure constant with a gas. So how do you keep the pressure constant? Well, something like you have a balloon that's open to the atmosphere. Since by open the atmosphere, it's surrounded by atmosphere, it's going to stay at constant pressure, atmospheric pressure. And then if you heat it, the balloon expands. If you cool it, the balloon contracts. So that's the kind of experimentation he was doing. And he found that the volume was proportional to the temperature. What units was he using for temperature?
Degrees Celsius. No.
He would have to be using something that's an absolute temperature. You can't use Celsius for things with the ideal gas law. You have to use Kelvin. And so he found that regardless of what gas it was, he had these straight lines when he graphed volume versus temperature if the pressure was constant. And further, he noted that they would all extrapolate to one point. That's how we got the first idea of an absolute zero, was that they would all extrapolate to one point. Now, do keep in mind, these dashed lines are extrapolations, and it wouldn't actually follow these dashed lines because at some point it's no longer going to be an ideal gas. If you get to colder and colder temperatures, you're going away from the ideal region. But because these extrapolate back to zero volume, that's where we get the concept of an absolute zero, because this was before they had the understanding of what temperature really was. It was just how hot something is. So Boyle's law boils down to V is proportional to temperature if you're holding pressure and the number of molecules constant. Or excuse me, Charles' law. Wow. Now, Gay-Lussac law, both Charles and Gay-Lussac worked on this. Actually, Charles worked on, I think, all of these. But Gay-Lussac's law says, let's hold volume constant instead of pressure constant. That bulb I had in here before was a bulb for testing Gay-Lussac's law. It holds the volume constant, and you can heat it up or cool it. And what he found was that as temperature went up, pressure went up, which is what we demonstrated when I brought that out in class. So we had Charles' law that pressure, let's just go back. Charles' law that volume is proportional to temperature. And then we have Gay-Lussac that pressure is proportional to temperature. And then we have Boyle's law, which is clearly incorrect here. What's incorrect about that? You could never have volume as inversely proportional to volume. That really wouldn't make sense. Volume is inversely proportional to pressure, or pressure times volume is constant if you keep the number of molecules constant and the temperature constant. Now notice Boyle's law, Charles' law, and Gay-Lussac law, they all kept the number of molecules constant. The final of the four laws that combine to give the ideal gas law is Avogadro's law that says the volume is proportional to the number of molecules if you keep the temperature and pressure constant. So if you take all of those laws and you relate them, you had pressure is proportional to temperature, volume is proportional to temperature. You can write a proportionality as pressure is equal to constant 1 multiplied by temperature. Volume is equal to constant 2 multiplied by temperature. If we go on to the third one, volume is inversely proportional to pressure. And then the last one, we can take these and combine them all together, and instead of having 4 different constants, we can just get one. And so if we combine those all together, notice this one here, V times P is equal to constant 3. And then since the other ones were holding P constant, we can say it's equal to constant 3 times, and we're going to have, temperature and N with other constants. I didn't write the other constants. And I just replaced this with some K for a combined constant that's combining the 3 constants into one. And I have what we call the equation of state for an ideal gas. It's an equation of state because a state is a specific value for the macroscopic variables pressure, volume, temperature, and number of molecules. So the ideal gas law, PV equals KNT, where K is a constant. K has a name. It's the what? The Boltzmann Constant, yeah. So that's the ideal gas law. Now, I heard some students saying, I'd like to be in general chemistry because, we all took general chemistry at some point in our lives, probably. In general chemistry, how did you write the ideal gas law? Lowercase n instead of capital N, capital R, and T. So if these two equations are both true, there must be a relationship between Kn and RT. That is, if these are both true, then you must have Kn is equal to Nr.
N's the same and the R and K just different place to write constant.
No.
Oh, yeah.
So, there we have the definition K, Boltzmann's constant. I didn't check this. Boltzmann's constant is now an absolute constant, and I forgot to check to make sure that it's still exactly that number. Because as of this past May, they've redefined things. So are you looking it up for me?
Yeah.
Okay, so Andy's going to tell us exactly what the Boltzmann constant is today, and if it's different than this, well, we'll change it. I'll actually keep talking. It is exactly that? Okay. So Avogadro's number. You probably all know Avogadro's number, 6.022 times 10 to the 23rd molecules per mole. Do you know where that comes from? Some dude named Avogadro? It actually comes, there's a number of ways you can come about it, but the way that I like to think about it is for relating mass of a molecule to mass of a group of stuff. And so Avogadro's number is basically such that if the mass of one atom of carbon 12 is 12 atomic mass units, then the mass of one mole is 12 grams. But it gives you a specific number. We talk about moles. Moles are just how many multiples of 6.022 times 10 to the 23rd do we have of molecules. And so the capital N is the number of molecules and lowercase n is the number of moles. And then Na, Avogadro's number, that's 6.022 times 10 to the 23rd. So given that relationship and the fact that we had to have capital NK is equal to lowercase nr, that means R is equal to capital NK over lowercase n. But from this relationship right here, capital N over lowercase n is Avogadro's number. And so R, which has some name like universal gas constant or something, R is just the Boltzmann constant divided by or multiplied by Avogadro's constant. So the version that's used most often in chemistry uses moles, and that's why you have R there. The version used most often in physics uses molecules, and that's why we have the K there. Did you find an exact number for it? No. Okay. Well, let us move on. A state is defined by those variables of state: the pressure, volume, temperature, and number of molecules. As you do problems in thermodynamics, you're often dealing with the change in pressure, temperature, volume, etc. And in those problems, it's easiest if you say, well, we're keeping the number of molecules or the number of moles constant. We almost always do that in physics. In physics, we use what we call a closed system. A closed system is where we put a cap on it, we put a lid on it, so the number of molecules doesn't change. In chemistry, they often use an open system. It's open to the environment so molecules can come in or go out. And that, of course, complicates things, having an open system versus a closed system. So our requirements are somewhat easier because of we can always put a cap on it. And so NR, using the ideal gas law, is PV over T. So when you're transitioning from one state to another, if the number of molecules stays constant, then you can just use PV over T equals PV over T. If you know all but one of those, you can calculate the last one. And when we get to thermodynamics, which is what we're morphing into, that's what we're going to do a lot of. Just to make sure we remember what an ideal gas is before we leave, I didn't set up a woo clap, so you just got to blurt it out. Which condition is necessary for the ideal gas law to apply? Only one of these is a correct statement. Well, we had a very strong and concerted A because that's the correct answer. The gas must be dilute. It must be a low density. Why must it be a low density? So the space in between molecules is large compared to the size of the molecule. So it's approximately the molecules have no volume. What was the other requirement? Okay, I thought I had another slide for the other requirement.
The other requirement was that it was completely elastic when they bounce off each other.
Yes, which we approximate by a temperature that's well above the condensation temperature. Okay, we will end at this point. I won't be here for lab tomorrow because of my wife's medical procedure, but Andrew will be here to run lab for you. So I will see you again on Wednesday. Yes.